Hey, I'm back with another evolution simulator video. Don't know what's going on then? Here's a quick recap. Have you ever wanted to feel like God? Well, with this you can kind of get the feel for it by overseeing the evolution of lots of these little creature things. Now these little guys have one goal, and that's not dying, which you could probably relate to. Dying does suck. But these creatures need to figure out how exactly you don't die with their AI neural network minds that can learn. And if they do live long enough to eat some pellets and then lay some eggs, they will hatch into the next generation to then continue the cycle yet again. And this goes on forever and ever till time itself has no meaning. Or you close the program. Okay, caught up? Let's go on with this. Now, the main subject of this video, optimization. This needs to run fast, as I've got big plans for this, and it can only go to 20 times speed. I hate waiting. You know that waiting a minute now means you have less minutes to wait for things in the future? It's a waste of time. So that's what we're going to be doing. Or I'm going to do that. Don't know what you're going to do. Okay, so the first step is going to involve fixing something that I've wanted to fix for a while now, but just kept pushing back. So everything in this simulation is stored in a big list called an array. Everything from food to creatures has its own array where every instance of a specific thing is stored. If I want to add some creatures to the simulation, I just add them to the array and just loop through all of them when I want to update their AI, position, state, or whatever I want. But there are two really big problems with this, as when you make an array, it has a fixed size, so I can run out of space when adding creatures, and I either have to stop adding creatures, or create a brand new, bigger array, and then copy everything over, which is really slow. But you could just make the array really big, and you won't really need to worry about that. What you can't avoid is what you need to do when removing elements. If I want to remove a creature, I need to first delete it from the array. It makes sense. But now I have this weird gap in the middle, which I can't have. So I now need to shuffle every single creature that's stored past it, one space forward, just to remove that gap. And for a simulation where there are a lot of food pellets that are constantly being eaten, memory has to be shuffled around constantly just to remove those gaps. So I'm going to replace all the arrays with these things called linked lists, which work up by being made of lots of nodes. A node stores two things: the data, the actual thing, like the food or creature or whatever, and where you can find the next node that stores more data. Adding data is really easy, as all you do is create a new node, find the previous last node, and just tell it to, store where that new node is. And removing data is a lot easier as before, as all you need to do is remove the node and all its data, and then find the node that used to point to it, and then just change that little bit so it then points to the next node afterwards. And then, boom, data deleted, no lots of copying needed. And after adding that, not much really change in performance. But I can now just add as much stuff as I want. No arrays mean no hard set limit to how many things there can be. It's a small change, but it makes it much nicer. So, what next? Well, I introduced to you something called the Entity Component System. Now, you might know this as Unity dots if you use Unity and code in that. But if you don't know what that is, then it's basically a way of storing and managing data that's better because it has a cool acronym. But my version of the Entity Component System is kind of like the Entity Component System, except without the components. It has entities in my version, but they're a completely different thing. It does have systems though. Now I'm not going to get into a lot of detail into the little differences and why my version is infinitely better in every single way, but the TLDR is that in a traditional Entity Component System that uses composition, you create entities that don't really store anything, and all the data is actually stored in components that you have to assign to that entity. And all an entity does is just keep track of which component it owns. And to do stuff to it, you have a system go through every component and do something to it. So a physics system would go through every physics component and calculate some physics stuff. Now my superior version that uses object-oriented programming has the entity actually store the data. So instead of just storing the components, it's actually made of the components. And a system will just go through every entity, but just look at the very small part that actually it cares about. It really is just a technical change that doesn't really mean anything, but I haven't really seen anything like it. Whatever, it's my video, I talk about what I want. Whatever, let's just add that. I think there was a good reason why people write entity component systems with composition, because going object-oriented made it a lot more complicated to code. But the end result is just pure art in how it works. Like, I had to do things that I didn't even know were possible in C++ to get it working. But now that it works, it also has the benefit of me also not needing to change the simulation code that much, as if I went with composition, then I need to rewrite most of it. But when making it, I found something really weird, as I ended up making two different versions of my version of the entity component system. The difference between the two versions does not matter at all, but the first version, when I ran it in debug mode, hit about 30 FPS, but when I let the compiler try optimizing that code a bit so it could run faster, which is something it can do, but it can't optimize everything, so I still have some work to do, the simulation hit about 60 FPS at 20 times speed, no problem, which was similar to how it was before I did all this optimization stuff. Now, the weird thing is that method 2 ran at 25 FPS in debug mode, so it must be worse, right? But when the compiler optimized it, the simulation could go up to 25 times speed. Strange. Well, with that done, the new ECS will let me add one very powerful feature: multi-threading. Since the dawn of man itself, people have always asked one question: why have one thing when you can have many things? The more stuff the better. That goes for everything except debt, taxes, and a couple other things no one likes. So in the simulation, I already put in a little trick called spatial hashing, which means that the entire world is split into a grid, so that everything in the simulation is in a specific grid square. So if I want to do something that only happens if two things are close enough, like collision physics, then instead of looping through every creature and checking every other creature to see if the two are colliding, I can just check the creatures in the nearby grid squares and ignore everything else and save a lot of time. Now, when I added this, it increased performance a lot, but why not, instead of checking one creature at a time, I do multiple? Now, I do already have a version of this I will not explain because it sucks and I'm replacing it anyways with a newer and much better way of multi-threading. So the way this all works is really simple. Well, the idea at least. Multi-threading is never simple to code. Okay, so you got your grid, and usually I would go through every grid square, update everything in there, and I'd move on to the next one. But now I have this group of threads that can do all the calculating for me. So what I do now is tell one thread to do the work in this grid square for me, and then I move on to the next square while it's still working, and I assign another one to that square. And I just keep doing this until I run out of threads, and at that point I just wait until one is done and I give him a new job. The idea is fairly simple, so this should be pretty easy to code. If anyone tells you multi-threading is an easy thing to do, go kick their knees in, because that's what a lying coward deserves. So just don't get me started on the nightmare I just went through. Okay, so the nightmare I went through all started right when I just added it, as it ran way slower than if I just did it single-threaded in debug mode, and when I turned off debug mode, then it just crashed, and for the longest time I had no clue what was happening. But whatever, I then fixed the crashing bug. But why was giving it more threads making it run slower? Okay, so a big problem for multi-threading is race conditions, and I'm not going to go into a lot of detail, but the number one rule of multi-threading is to make sure two threads don't access the same data at the same time. And that happens a lot in the simulation, as, for example, physics, a creature will not only have to check the grid it's in, but it will also have to check everything in the surrounding grids, because that creature could technically be in one grid, but have its hitbox be in the outside grid, so it will also need those outside grids checked. And because it checks both the grid it's in and the surrounding grids, you can get two threads accessing the same data and trying to edit it at the same time, which you do not want ever. Now, to make sure that never happens, I have it so that if one thread is touching data in one grid, then it locks it and no one else that wants that data can access it. They just have to wait until, well, that thread's done with it, and then it can unlock it. But the problem is that locking a grid is really easy, but when a thread wants to access data from a locked grid, it goes to sleep until it gets unlocked, which doesn't sound that bad, except when that happens, the operating system goes, oh wait, you're not using them? I'll just borrow him for a second to do some stuff for some other programs. Don't worry, I'll return him all fine, and by the time you get your thread back, it's already late and the cache has been wiped, which slows everything down. And because of how I set everything up, threads get locked constantly. So instead of going through every grid one by one, I'm gonna now go so that the program now just sends off a random grid, not sequentially anymore, so it's less likely to choose one that has locked grids next to it. Huh. Still slow. Wait, why is that now? So this program wasn't even multi-threaded because I only gave it one extra core? Whatever, click, now it's on. Wait, what? No, why is it going slower? Oh, come on, why is this happening to me? What did I do so wrong in a past life to make this so hard? I've probably messed up my code so badly that if I remove all the multi-threading stuff, it'll run even slower than before I even added it. Wait, how did I make single threading faster by complete accident? The sim can go twice as fast now. I should feel happy about this, but I feel nothing. Whatever, anyway, let's just continue. Okay, so remember how I said earlier that locking data can slow everything down? Well, the code for managing the threads and giving them jobs also uses those locks. So every time a thread finishes its job, it has to go through tons of different locks just to get to the next job, and the code I have creates a little over 1,000 jobs because each grid of a specific entity type requires its own job. So okay, quick fix, now the program sends these new big mega jobs to the threads, which now start to calculate big chunks of the world at a time instead of just one tiny smidgen. And because I'm doing that, no more random grid access, just to reduce how many grids will get accessed by multiple threads at the same time, and cause thread sleeping, as I'll need locking but not as much. And it still runs slower. Not by much, but slower. Maybe I'm going at this all wrong. The big thing slowing this down is thread locking, because the operating system just loves to steal away resources. Every time I've tested this, it's always been on the same world size. So maybe it's just that while it's faster, it's just not noticeable at this world size, and that if I make it bigger, I can actually notice the improvements and it's actually faster now. Okay, that's more like it. Damn, that's pretty big. And it's going pretty smooth. Now I'm done with multi-threading. Good to know that all this time I put into this wasn't a complete waste. Also, a funny thing, now that I put the simulation big enough, the GPU has started to struggle a bit. Not from the complexity of the graphics, like, come on, it's flat shaded pixel art, but because of just how much stuff there is to draw. Easy fix just made it so that I only draw stuff that's visible to the screen. And a few more tweaks later, so that the grids are only accessed when they're needed, and I am done. But okay, how much faster is all this? Well, imagine that this thing here is as big as the world that I used to run. Now this is how big it was with just the compiler optimizations. And this is how big I can make the world now. Pretty big, huh? Like, look at this. It's almost stupid how big the world size can be. Like, there's almost no point at all. Like, an entire creature could probably spend its life just in one tiny section and not even know that there's like massive chunks of the world it's never even known, or even like ancestors have even seen. Oh look, it's the end of the video. So thanks for watching this far. Now, in the next few videos, this evolution simulator will change or evolve a lot, as all this optimization stuff is to make room for the creatures evolving more complex bodies. So stick around for that, as I got plans for that, and I am praying that they all work, as it's gonna get weird. So anyways, join the Discord server, comment something, subscribe with the bell button on to make the algorithm like me more, and see you in the next video.